Welcome to MarkScheme. Forces and momentum. Everything you need made visual. Here's a question that decides whether you walk away from a car crash. A car has a certain momentum, mass times velocity. And in the crash, that momentum has to drop to zero. The seatbelt and airbag cannot change how much momentum you lose. So what do they actually do? They stretch the crash out over more time. The force you feel is the change in momentum divided by the time it acts. Spread the same momentum change over a longer stop, and the force drops. That single idea, force is the rate of change of momentum, is the heart of this whole topic. Let's build it properly. Here's exactly what this covers. Straight from your syllabus. IB Physics, Theme A, Subtopic 2. Newton's 3 laws and free body diagrams. Every kind of force, weight, normal, friction, tension, springs, drag, buoyancy. Newton's second law in both its forms. Momentum and impulse. Conservation of momentum through collisions and explosions. And circular motion. Here's the good news, and it's a big one. Every single part of A2 is standard and higher level common core. There is no higher level only content here. All of this is on both the SL and the HL papers, so this one video serves both. Everything rests on Newton's 3 laws. Law 1, if there's no net force, the velocity doesn't change. A body at rest stays at rest, and the body already moving keeps moving in a straight line at constant speed. That reluctance to change is inertia. Law 2. A net force produces acceleration. The sum of the forces equals mass times acceleration. This is the one you'll compute with constantly. Law 3 is the subtle one. Forces always come in pairs. If body A pushes on body B, then B pushes back on A with an equal and opposite force. The crucial detail, and where marks are lost, is that these two forces act on different bodies, so they never cancel each other out. A rocket pushes gas backwards. The gas pushes the rocket forwards. Before you write a single equation, you draw a free body diagram, and doing this well is worth easy marks. The recipe. Shrink the object to a single dot. Then draw only the forces acting on that object, each as an arrow starting from the dot, pointing the right way, with a length that hints at its size. Watch it assemble on a box being pushed across a rough floor. First, weight. Gravity pulls the whole mass straight down, equal to mg. Then the normal force. The floor pushes back up, perpendicular to the surface. Now the push we apply, driving it to the right. And finally, friction, opposing that motion, pointing left. 4 forces, 4 arrows, all from the one dot. That picture is what turns a wordy problem into simple equations. Let's catalog the forces themselves. Weight is mg. Gravity acting straight down. The normal force is the contact push from a surface, always perpendicular to it. Friction opposes relative motion, and note the two cases. Static friction can take any value up to mu times the normal force, holding things still, while once the object is actually sliding, dynamic friction is fixed at mud times the normal force. Tension is a pull transmitted along a rope or string. A spring gives a restoring force following Hooke's law. F equals kx. The more you stretch it, the harder it pulls back. Viscous drag resists motion through a fluid and grows with speed. And buoyancy, or upthrust, is the upward push. A fluid gives a submerged object. Every one of these, but the normal tension and drag, has a formula in your data booklet. You don't memorize them. Now the two situations. If the forces on a body are balanced, they add to zero. The body is in translational equilibrium. That does not mean it's stationary. It means the acceleration is zero. So it's either at rest or moving at constant velocity. Sum of forces equals zero. But if the forces don't balance, there's a net force. And Newton's second law kicks in. That net force equals mass times acceleration. And the acceleration points the same way as the net force. The method is always the same. Resolve the forces into x and y, add them up in each direction, and solve. That's the engine of nearly every mechanics question. Momentum, symbol P, is mass times velocity. It's a vector. It has a direction. And that will matter enormously in a moment. Now watch something beautiful. Start from F equals ma. Acceleration is the change in velocity over time. So this is m times delta v over delta t. Pull the mass inside. It's the change in mv over time. The change in momentum over time. So the second law has a second, deeper form. Force is the rate of change of momentum. Rearrange it, and you get impulse. Force times the time it acts equals the change in momentum. That's the seatbelt from the start. Same change in momentum. But a longer time means a smaller force. And because impulse is force multiplied by time, on a force time graph, the impulse is simply the area under the curve. Here's the crown jewel of the topic, and it comes straight from Newton's third law. In any collision or explosion, as long as no outside force interferes, the total momentum of the system is exactly the same before and after. Watch. Cart A rolls to the right, with some momentum. Cart B sits still. The green bar at the top is the total momentum of both carts together. Keep your eye on it. A catches up to B, and they collide. Afterwards, whether they bounce apart or stick together, the momentum simply redistributes between them. Sum of A's momentum passes to B, but add the two together, and you get the identical total. The green bar doesn't so much as flicker. Momentum is neither created nor destroyed, only shared out. Now, the vital distinction. Momentum is conserved in every collision, always. Kinetic energy is not. In an elastic collision, kinetic energy is also conserved. Think hard, bouncy balls. In an inelastic collision, momentum is still conserved, but some kinetic energy is lost to heat, sound, and deformation. And if the objects stick together, that's perfectly inelastic. The biggest loss. An explosion is a collision run backwards. Something at rest, total momentum zero, bursts apart, and the pieces must fly off, with momenta that still add to zero, one way balancing the other. Here, kinetic energy is gained, released from a store. The takeaway to burn in. Momentum is conserved in all of them. The kinetic energy check is what tells elastic from inelastic. Last piece. Circular motion. A ball whirls around on a string at steady speed. Its speed is constant, but its velocity is not. The direction keeps changing, so it is accelerating, and by Newton's second law, that needs a force. Which way? The velocity always points along the tangent, but the force points inward, straight to the center. It's called the centripetal force. And here it's the tension in the string. Notice the green arrow. As the ball goes round, it swings to keep pointing at the center the whole time. That is the signature of circular motion. The size of the inward acceleration is v squared over r, or omega squared times r. where omega is the angular velocity, 2 pi over the period. Multiply by the mass, and you get the centripetal force, mv squared over r. Cut the string, and that inward force vanishes, so the ball flies off along the tangent, not outward. Time to use it. Example 1. All my own numbers. A 5 kilogram box is pushed along the floor with a horizontal force of 30 newtons. The coefficient of dynamic friction is 0.3, and g is 9.8. Find the acceleration. Step 1. Always. The free body diagram. Weight down, normal up. The 30 Newton push right. Friction left. Vertically, the box doesn't accelerate, so the normal force equals the weight, mg, which is 49 newtons. Friction while sliding is mu d, times that normal force. 0.3 times. 49 is 14.7 newtons. Now the horizontal net force. 30 minus 14.7 is 15.3 newtons. Divide by the 5 kilogram mass, and the acceleration is about 3.06 meters per second squared. Example 2. A collision. A 2 kilogram trolley moving at 3 meters per second runs into a stationary 1 kilogram trolley, and they stick together. Find their common velocity, then check the kinetic energy. Conservation of momentum first. The total before is 2 times 3 plus 1 times 0, 6 kilogram meters per second. After, the combined 3 kilograms move together at v, so that's 3v. Set them equal. 3v equals 6, so v is 2 meters per second. Now the kinetic energy check, and this is the mark students forget. Before, 1/2 times 2 times 3 squared is 9 joules. After, 1/2 times 3 times 2 squared is 6 joules. 3 joules have vanished into heat, sound, and deformation. Kinetic energy is not conserved, so this collision is inelastic. Momentum survived. Energy did not. Example 3 brings back the force time graph. A 200-gram ball starting at rest is struck by a force that ramps up to a peak of 30 newtons and back down to 0 over 4/10 of a second. A triangular pulse, like a racket hitting a ball. Find the impulse, then the speed the ball leaves with. The key idea. Impulse is the area under the graph. The area of the triangle is 1/2 times the base times the height. 1/2 times 0.4 seconds times 30 newtons here, which is 6 newton seconds. That impulse equals the change in momentum. The ball started from rest, so its change in momentum is m times delta v. Divide 6 by the 0.2 kilogram mass, and the ball flies off at 30 meters per second. Example 4. Circular motion. A 1/2 kilogram ball on a 1 meter string is swung in a horizontal circle at 4 meters per second. Find the centripetal force. Straight from the data booklet. The force is mv squared over r. Substitute. Mass 0.5. Velocity 4 squared is 16. Radius 1 meter. 0.5 times 16 is 8. Over 1 is 8 newtons. And don't forget the direction. It points to the center. And here, that force is simply the tension in the string. 8 newtons inward. Now, the exam craft that separates the top grades. 1. Draw the free body diagram first, every single time, and list every force on the body. A missing arrow is the number 1 way to lose the whole question. 2. Momentum is a vector. Choose a positive direction and give anything moving the other way a minus sign before you add. Forgetting this wrecks collision problems. 3. If they ask whether a collision is elastic or inelastic, do the kinetic energy check. Elastic means it's conserved. Inelastic means it isn't. 4. Impulse is the area under a force time graph. So break odd shapes into triangles and rectangles. And 5. All of these equations live in your data booklet. So don't waste effort memorizing. Learn to find them, quote the formula, then substitute. That habit alone banks method marks. Finally, the 4 traps that quietly cost marks. 1. Leaving a force off the free body diagram. Or worse, inventing a force of motion, pushing the object along. There's no such thing. 2. Treating momentum as a plain number and ignoring direction. Anything moving the other way needs a minus sign. 3. Assuming kinetic energy is conserved. It only is in an elastic collision, so always run the check. And 4. Drawing the centripetal force pointing outward. It always points inward to the center. Dodge these 4, and A2 becomes reliable marks. And that is A2, forces and momentum, fully covered. Newton's 3 laws, free body diagrams, every force type, F equals ma, and F equals the rate of change of momentum. Impulse as the area under a force time graph. Conservation of momentum through collisions and explosions. And circular motion with the force always pointing to the center. Every part of it sits on both the standard and higher level papers. Next in the course, we follow the energy, work, energy, and power. For more, that's MarkScheme.app. See you there.